Good day, everyone. I'm pleased to share our research entitled Analysis of Optimum Negative Emission Technology or NETS Portfolios Using Space Filling Design of Experiment Strategy. My name is Maria Victoria Amigo Sumagang from the University of the Philippines, Los Baños, and my co-authors are Professor Raymond Tan and Professor Kathleen Aviso from De La Salle University. The presentation is divided into 5 parts, and we will begin with the introduction. There is undeniable scientific evidence that human-made emissions are causing global warming, and the modeled pathways show that emissions need to peak by the year 2025 and reach net zero by the year 2050. And without our action, global warming will cause extreme weather events that intensify as the temperatures increase. And we have seen the increasing frequency of these extreme weather events all over the world, such as flooding and super typhoons. Aside from the traditional decarbonization options like renewable energy, etc., negative emission technologies or nets that remove carbon dioxide directly from the atmosphere are now needed to biophysically and economically achieve net zero emissions. However, these nets will consume resources that may compete with other societal priorities. Thus, net portfolios that recommend a technology mix of individual nets at smaller scales are preferred to lessen the environmental and social impact. These concerns present the need for integrated net portfolios that optimize resource consumption, and process integration can help with that. Process integration is a subfield of process systems engineering that deals with the integration of whole processes to reduce resource consumption and emissions. And among the techniques used in process integration, mathematical programming can handle the different tasks such as simulation, optimization, design, selection, and ranking of net portfolios. Mathematical programming has been used in optimizing net portfolios under multiple resource constraints. But for regional scale applications, the uncertain resource constraints highly depend on local conditions and the decision maker. And these uncertainties have to be investigated. And one way to consider these uncertainties is through post optimization sensitivity analysis. And the most common is to see the effect of the optimum on the optimum objective value by varying one factor at a time. Commercial solvers also make use of the dual price value, which is the amount of increase or decrease in the objective per increase in the constraint. For nonlinear models, Lagrange multipliers can also be used. However, the disadvantage of these approaches are that the interaction and higher order effects are not captured in the analysis, and they only investigate the changes of the objective value with respect to small changes in the parameters. To address these limitations, the traditional sensitivity analysis can be replaced by a global sensitivity analysis using a space filling design of experiment strategy. Um, this is done by performing computer experiments on each of the point in the design space. The advantage is that this approach is not limited to investigating small changes in the parameters, and it evaluates the combined effects of the parameters. Therefore, the knowledge gaps identified in this work are: first, there are limited studies on net portfolio optimization considering resource constraints. Next is the traditional sensitivity analysis applied have disadvantages, and to address these knowledge gaps, this work's objectives are: first, to develop a novel mathematical programming model for optimizing net portfolios and to illustrate a model in a case study. Second, to perform a global sensitivity analysis using a space-filling design of experiment. This study contributes to the development and analysis of optimum net portfolios for emissions reduction planning. Moving on to the problem statement and an overview of the methodology. Given a set of nets and a set of resources, their specific constraints, given the other model inputs and targets, the problem is to build an optimization model that defines the objective function f of x, where x is the decision variable, in this case the resource constraints. The optimization model should be subjected to a global sensitivity analysis by varying the decision variable using a space-filling design of experiment strategy. First, the performance of the computer experiments is done, and then next is the regression analysis of the optimal solution f of x star as a function of the decision variable is estimated. Moving on to the methodology, the optimization model is a multi-period fuzzy mathematical programming model. And the advantage of a fuzzy model is that it can handle multi-objectivity. The FMP model aims to maximize the net present value of the net portfolio and also simultaneously maximizes the negative emissions capacity of the portfolio within the fuzzy intervals. In addition, it minimizes the resource consumption within the fuzzy intervals. So, Lingo is used to program and solve the model. For the global sensitivity analysis, the factors are the resource constraints, which are land, water, energy, and nutrients, and the responses are uh, negative emissions potential and the net present value. The following step is to define the factor space or the upper and lower bounds of the resource constraints wherein sampling will be made. Using the space filling design Latin hypercube, sufficient points are sampled to satisfy the degrees of freedom for the statistical analysis. And the DOE is made using the software that is 360. The model is then evaluated for each design point through computer experiments. Finally, a regression analysis is done to give a statistically significant polynomial regression model that closely resembles or closely approximates the true response surface of the model to varying resource constraints. And this is the regression analysis is done through the help of the software studies. For the case study data is based on an existing study. 6 terrestrial nets are considered and their data are shown. And the multi-period resource constraints are also shown as well. You may use the QR code or the link to view the data for this study. The results are shown for the response, negative emissions potential, and the net present value. The effect of the resource constraints are shown for each response. So for land, water, energy, and nutrients, the corresponding letters are in the legend. The generated LHD or Latin hypercube design has 16 design points and can detect linear two-factor interaction and quadratic effects. So terms that have a p-value less than 0.05 are statistically significant, while if it's greater than 0.05, it's statistically insignificant. The signs, whether positive or negative, indicate the direction of the effect. And we can see from the tables which effects are significant and which effects are insignificant. For the negative emissions potential, the relationship is just linear because the quadratic effects are insignificant and also the interaction effects are insignificant. For the response net present value, we can see that some interaction and quadratic effects are significant. The response surface graphs are also generated for each response. So the advantage of performing this kind of analysis is to consider the higher order effects like quadratic effects and the interaction effects. For example, the results show a negative interaction effect between land and water on the net present value, and also a negative quadratic effect of water on the net present value. So these interactions and curvature are not detected in traditional sensitivity analysis. Doing this uncovers more insights than the traditional sensitivity analysis. For example, the interpretation for the negative interaction effect between land and water on the net present value means that as we increase both land land and water limits, the corresponding increase in the NPV is less than what could have been their sum if their limits were increased individually. Hence, the decision maker may focus on increasing the land or water constraint, but not both. And the negative quadratic effect of the water limit on the net present value means that increasing the water limit only benefits the net present value up to a certain point, and further increase negatively affects the net present value. Moving on to the conclusions. In conclusion, this study meets two objectives. The first is the development of a novel and mathematical programming model for optimizing net portfolios and the illustration of the model in a case study. Second, the performance of a global sensitivity analysis through a space-filling design of experiment that this uncovers more insights than the traditional sensitivity analysis. Again, this work contributes to the development and analysis of optimum net portfolios for emissions reduction planning, future work, and investigate the effect of other factors on the responses. If you are interested in the other optimization and decision support models for deploying nets, I would like to invite you to view our review paper using the QR code or link. It's open access. Thank you very much. Comments and questions are welcome. You may contact me using this email address.